Okay, here's another example of rigid body kinetics. This is again a pulley problem. So let me draw the pulley setup. A pulley like so is attached to the ceiling by some support like that, and a rope goes over the pulley, and one side of the rope is being pulled down with force F, and the other side of the rope is attached to a mass M. The pulley itself has mass M1. So this is the statement of the problem. Pulley mass radius R. It's a uniform disk with moment of inertia so if you say this point is G, inertia Ig, so this is all given. Ig equals mr squared divided by 2. And rope is massless and inextensible. But the pulley, unlike our old problems, does have mass. It's got it's a uniform disk, has mass, has moment of inertia, and so on. Okay, I said I guess mass m1, radius r. Okay. Okay, so that's given. Let's say the force F is known, the mass m2 is known. Determine again. So now I'm going to ask a few things. Acceleration upward of m2. Angular acceleration alpha of pulley. Let's say this is part A, part B. C, tension in rope attached to M2. Okay, so basically, what is the tension in this rope? There's a subtlety here. And D, reaction force between pulley and the ceiling. In other words, if there's a reaction force in this support, what is the reaction force that is holding the pulley up is what I'm asking here. Okay, so I would like to find all these things. Okay, what is the first step in all these problems is to draw free body diagrams. Now we have more than one object which has mass. We have mass we have a pulley which has mass, but we also have this other mass, which you can treat as a particle in that we're not worried about it rotating. The pulley we're worried about rotating, but for this mass you can just treat it as a particle. All it's going to do is move up or down. The pulley is going to rotate, so we got to consider it to be a rigid body. Okay. In any case, let's draw free body diagrams. Let's draw first for the pulley. That's the pulley. We have a reaction force pulling up, which is what's being asked in part D, and mass of the pulley pulling it down, and we have a tension in this rope, which I'm going to call T, and then a force F, which is essentially tension in this rope. Okay, now in the old problems so far in the course, if we had a massless rope going over a massless pulley, we assumed, or we showed actually implicitly, that the tension along the string is a constant. The tension here would be the same as the tension here. But if we have a massive pulley, in other words, a pulley with mass, then it turns out the tension on the two sides of the pulley need not be the same. Okay, need not be the same. In fact, so that's why we are assuming that they're actually different, and we will show that in fact assuming that will result in T actually not, well, we are assuming that they can be different, and we will find that they are in fact different. Okay, so that's the free body diagram for the pulley, and then the free body diagram for the mass M2 is going to be M2G like so, and T like so. Okay, for some of these problems, there's always a temptation to say T equals M2G. That is not true. In fact, it is the difference between T and M2G that is actually making this mass accelerate up or down. T equals M2G would be a statics problem. This is a dynamics problem, and it's not in general true that the tension equals that mass times gravity. Okay, so those are the two free body diagrams. So that's step number one. What's step number two? Is essentially using F equals ma and the sum of moments equals I alpha. Use F equals ma. Let me put that in quotes. And sum of moments equals I alpha. I'm sort of putting it in quotes because I'm just sort of writing that roughly. Okay, so let's do F equals ma for this mass. So let's say, let's define some notation here for acceleration. Let's say the acceleration of this mass is upward positive and a, and let's say the angular acceleration of the pulley is anticlockwise and alpha. Okay, let's say that. So what do we have? We have for pulley, if this is the point G, sum of moments about G equals IG alpha K, or basically mr square divided by 2 alpha K. And what is sum of moments about G? What are the forces here? We have force F with this momentum R. So we have Fr times K. We have this tension, which is, so the Fr is an anticlockwise moment. So anticlockwise moment is considered positive and in the K direction. T, the tension T is is clockwise. So that's going to be minus TRK. Okay. And those are the only two moments. The other two forces are R. Maybe I shouldn't have called it R. Maybe I should call it N or something. So let me actually erase this because the radius is also R. Okay. But in any case, let's, yeah, so everything else is fine now. Um, so that's the sum of all moments. So we just equate these two things. So we have FR minus TR K equals MR squared divided by 2 alpha K. Everything is in the K direction, so the K sort of drops out. So what we have is F minus T R equals MR squared by 2 alpha. This gives us alpha equals 2 F minus T divided by MR. Okay, this is not the answer yet, although it's a useful equation. So this is, let's call this equation number 1. This is not the answer yet because we do not know what the tension is. We've written the angular acceleration in terms of the tension T, but that's also an unknown, tension of the rope attached to M2. Okay, so let's continue. So all we've used is sum of moments equals I alpha, and we've gotten one relationship. We can do sum of forces equals ma for this mass. We can also do sum of forces equals ma for this mass. Okay, so for pulley, again, sum of forces equals m1 ag, right? So what is the acceleration of this point g? It's going to be 0 because the pulley is just stuck in place. So all these, so what's the acceleration of point g? It's going to be 0. So all these forces need to essentially sum to 0. So what do we have? N minus F minus m1g minus t. Okay, so let's do that. Equals m1 times 0 because the pulley is not going anywhere. So that's equation number 2, let's say. Basically that n minus m1 g minus f minus t equals 0. Okay, that's equation number 2. For mass m2, we can have a similar equation. We have, what do we have? We have a force T minus m2g equals m2a. Okay, we have that. T minus m2g equals m2a. Okay, now something else I did not say yet, but I'm going to say now. Okay, let's first look at, do we have enough equations in all the unknowns? How many unknowns do we have? We have unknowns. We have unknown, well, alpha. We have A. We have the tension T. And we have the normal reaction or the reaction force N. So 4 unknowns. And we have 3 equations so far. Now we need one more equation. What might that equation be? I actually have not stated it, but in all these pulley problems, or at least many of these pulley problems, we will state that the pulley, the rope of the pulley goes over the pulley without slip. In other words, there is no rubbing between the pulley and the rope. Another way of saying that is, let's say this point of the pulley moves down with a particular velocity. Every point on this point on the rope moves down with a particular velocity. Every point on the rope here will move down with the same velocity because the rope is inextensible. And then there's a point here on the rope which is just in contact with the pulley. That point and the pulley, that point on the rope and the point on the pulley will have the same velocity. That's what moving with no slip means. Same for this point. Okay, so what does that mean? It means that actually the velocity of that point, which is, if you have an angular velocity omega, Um, so if rope has no slip, relative to pulley, then let me draw a picture of the pulley. And let's say this point is G, this point is P, and let's say we have angular velocity omega of the pulley. Vg, of course, is 0 because G is not going anywhere. Vp, let's say, is basically velocity up like this. And Vp, because P and G are in the same rigid body, it's basically going to be Vp equals Vg plus omega cross Rp with respect to G. And that's going to be equal to 0 plus omega k cross Rp with respect to G is going to be Ri, and that's going to be equal to omega R. K cross I is J, so R omega J. That's going to be equal to Vp J. So Vp equals R omega. And what's going to happen is the acceleration of mass m2 is basically a, which is going to be equal to AP, at least in the tangential direction. So A will be equal to AP, which is going to be equal to R alpha, okay? Where AP is the tangential acceleration of point P in this direction. So that's what we get. A equals R alpha because of no slip. Okay, so this is equation number 4. This equation essentially completes the set of equations that we need. We have four unknowns that we said, and 3 equations so far, and this makes it the 4th equation. Okay, let's now try to solve all these equations. Let's see. Let's plug equation 3 in equation, let's say, 1. So let me just write all the equations again here. One of them is alpha equals two f minus t divided by mr. Equation number 2 is t minus m2g equals m2a. Equation number 3 is all these things, n minus equals 0, and equation 4 is a equals r alpha. Okay, so let's solve these things for all the unknowns. How do you do that? First of all, we can either solve for a or alpha. Let's actually perhaps solve for a first. So rearranging 1, so 1 implies r alpha equals 2 f minus t divided by m, and then 4, using 4, you can essentially plug in r alpha equals a. So you get A equals 2 F minus T divided by M. And then we can then substitute equation number 2 in there. So A equals 2. So basically, let me erase this first. 2, if you rearrange it, implies T equals M2G plus M2A. And then we plug that back into this thing. Let's call that 5. So we have A equals 2 F minus M2G minus M2A divided by M. Now let's see if we can substitute things. Rearrange this a little bit, bring the M up here. Well, what M is this? This is going to be M1, M1, M1. So we have M1A equals 2 F minus M2G minus M2A. We can bring this M2A to the other side, so M1A plus 2 M2A equals 2 F minus M2G, or A equals 2 F minus M2G divided by M1 plus 2M2. Okay, so that's what we get. So that's the acceleration. Alpha is going to be A over R, so that's going to be 2 F minus M2G divided by R, M1 plus 2M2 is what we get for angular acceleration using 4. So these are all answers. And then now we can relatively easily plug in those things into these equations. Now that we know A, we can plug it into this equation to get T. So we can just plug this into this equation to get T. And then if you know T as well, we can compute N. So I will just leave that exercise. Use 2 and 3 to compute. Plug these results in 2 and 3 to compute and so first I guess we do T and then N. So and then that's it, done.